Hello guys and welcome to another session where we are looking at another paper here today. This is going to be the last of our formal sessions. Hello, 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 hello. Is it fine now? All right. So we are starting with this paper 61 of winter. So let's get started with this. This is going to be our last formal session, after which we'll have the AMA tomorrow because your paper is then the day after. So it's on the day after today, so 13th of May. So this is the last paper that we are looking at, and this is ATP. So let's get started. So if you remember, then this paper is really similar to the one which came before. A student determines the weight of a meter rule using a balancing method. 1.1 shows the setup. So the student places the meter rule on the pivot. She places the load P on the meter ruler at the 90 cm mark. She adjusts the position of the meter ruler on the pivot so that the meter rule is as near as possible to being balanced. Right. So in that, the question one was also on balancing a meter rule. This is also pretty similar. The ruler balances with the pivot at the 75 cm mark. Right. So with the pivot here, so you can really adjust the pivot. And when the pivot is at 75 cm with the load here, this is where it balances. It first says calculate the distance A from the 90 cm mark to the pivot. So this is 90, this is 75. Subtracting the two, I get my value of A. And this is supposed to be recorded in a table, right? So let's see here. So the ruler balances with the pivot at the 75 cm mark. So this means this is 75, right? And we are talking about A here. So from the 90 cm mark to the pivot, so A is supposed to be, all right, let's see. Hmm. Yeah, so A is supposed to be 15.0, right? 19 minus 75. This turns out to be 15.0 centimeters. She records in table 1.1 the distance B from the pivot to the 0.0 cm end of the meter ruler. She repeats the procedure by placing the loads at different values. This is exactly what was happening there as well. And also in this case, you are supposed to draw a graph as you were supposed to do it there. So you have A on the y-axis, B on the x-axis, and you are supposed to start the y-axis at 0, right? So from 0, I have to go up to exactly 15. So let's see what values I could take. So maybe something like this, that if this is 2.5, this is 5, 7.5, 10, 12.5, 15. So this is good enough, right? So first off, let's just label our axis, which is in this case A in centimeters. And this starts from 0. So this is 0.0. This is 2.5, 5.0, 7.5, 10.0, 12.5, and 15.0. Usually it's good practice that even if you do not use the rest of the grid according to your values, should number this as well. This would be 20.0. Right, so this is how the values are. All right. Then for the B axis, we don't really have to start it at 0.0. It was up to us. So we could use a false origin if we want to. Let's see what B values are like. So they start from 62.5, go all the way up to 75. So I'm thinking the same that if we take 60 to 75, so you see these values are also going from 0 to 15. These can also go from 0 to 15 with 60 up to 75. So if I also look here, let's take this value as our 60, and then I have to go up to 75. So if this is our 60.0. So if this is 62.5, 65, 67.5, 70, 72.5, and 75. So this is pretty neat. Let's do this. 62.5, 65.0, 67.5, 70.0, 72.5, and 75.0. And now this is when we start plotting our points. So first value is A15 and B75. So A15, B75, that's going to be this value right here, right? This is the value I've marked. Do it again. All right. Now, in reality, you should not blob your dot this much. I'm doing it here on purpose, just so that you guys can see my points. But if in a paper, if your size of the dot is greater than half a small square, you will lose values. So even right now, I'm also on a very thin line between losing and gaining marks because my dot is just slightly under half a small square. A 13.1, B 71.9. So 13.1. All right, so this would be 13, 13.5. All right, so this would be 13, 13.5, 14, 14.5, 15. So this is not right, obviously. So this means that this would have to be stretched out twice. So each two boxes are 0.5. So 13, 13.5. Now, because I want to plot 13.1, so this is slightly above the 13 line, and my x coordinate is 71.9. So this is also slightly tricky to look at, but still, let's try our best. So this is also the same scale, 70.5, and this would be 71. So 70.9 is almost this line right here. And we had 13.1, so almost here is where our point should be. 70.9, 13.1, be slightly here. So this is another point. All right. Next we have 11.3 and 68.8. So 11.3, 68.8, 68.8. So this would be 68, and then this would be 68.5, and then this would be 68.5, and then 69 and 69.5 and 70, right? So again, let's see here. 68, 68.5. What did we have to plot? We have to plot 68.8. So I'm thinking right in the middle of both of these boxes. So 68, 68.5, and this would be our 70, right? So right in the middle, this is almost a 68.8, and the other value is 11.3. So 11.3, let's see. 10.5, 11, so 11.3 would be here as well. Again, I think that maybe we could have done better with our choice of scale so that we got really easier values to work with. But again, now that I have marked it, I have to go through with it as well. 9.4 and 65.6. 65.5 would be here. So 65.6 would be slightly ahead, and 9.4. So 9.4. So this would be 9.5. So 9.4 would be slightly here, right? And then what else do I have here? 7.5 and 62.5. So these ones seem very easy compared to the other ones. So it's this one. Right, so now it appears obviously that all of these lines are on a straight line. So 1, 2, 3, 4, and 5. In a previous case, if you remember the previous paper, the lines were not really on a, the lines were really not lying on the same straight line, but still the examiner was wanted us to draw. In that case, the points were very clearly lying on a curve. But still the examiner used the word for us to draw it on a line, right? So regardless of what the examiner says, always also use your own common sense and see whether the lines are on a curve or on a line. Obviously, there can't be three anomalous points when we're talking about a line. There has to be only one in a worst case, which is almost never going to happen. But I'm just talking about the worst case here, right? So here we just have to draw a line now. Let's draw that line. All right. So probably I could do slightly better here. Yeah, this seems about right, because we have a point above, a point below, and all of these is almost exactly on the line. So this is my line of best fit. Determine the gradient of the graph. So gradient of the graph, show clearly on the graph how you obtain the necessary information. So this is just talking about the point. And whenever you are expected to show that these points on the graph, so do draw a small triangle to show what points you selected. So let's say one of my points is this one right here, and another one is, let's say, this right here. So what I should now do is draw a triangle. And now I should just read off the coordinates. So this one is really easy to look at. X coordinate is 65.0, and the Y coordinate we have to read off. So this would be 10, so 9.5. And this is halfway in the middle, so this would be 9.25. Right, so this is 9.25. So for this one, I would need to complete the labeling. So to complete the labeling, this would be 77.5, and this one would be 80, right? So 80 minus 0.5, this would be 79.5. Just a second, I think I've taken up wrong values here for the scale. So this one was 65 and it can't be 9.25. All right. So this is 7.5. So this is 8, 8.5, 9, 9.5. Actually, 7. So this is 8, 8.5, 9, 9.5, and 10. So 9.5 and 9 point. Yeah, so this was 9.25. Is that what I've written? Yeah, that's fine. So here as well, this is 80. So if I look at this here, so 78, 78.5, 79, 79.5 is what this value is. So x coordinate is 79.5 and the y coordinate so this is 17.5 and 18, and this would have been 18.5, so this is 18.25. Okay, so this is the difference a good scale can make. Not to say this scale is incorrect, but if you took an easier one where we did not have differences of 0.5, so it's just going to be slightly easier. So change in y is 18.25 minus 9.25. 18.25 minus 9.25 divided by change in x, which is 79.5 minus 65. So what does this turn out to be? Let's see. 18.25 minus 9.25 is 9 over 79.5 minus 65, which is 4.5. Again, I don't have my calculator today, so 9 divided by 14.5 is 0.6206. 3SF is always a safe bet when talking about calculated values, either in your structured questions or in your ATPs. So I've written this to 3SF. Weight of the meter rule is numerically equal to 2g, so I just double my answer. Turns out to be 1.241 or to 3SF 1.24, and this is the weight. It's up to me to give the answer, to give the correct unit. So that's 1.24 Newton. In this case, the examiner was accepting answers in the ranges 1 to 1.4. So just one possible reason, one practical reason why it is difficult to obtain readings for A and B. So for A and B, again, we also talked about this, which is that the masses can move. Also, it's difficult to read from the center of the load to judge the center of the load. And also it's difficult to obtain the balance, right? So it's the exact 3 reasons which were written there that we're also going to talk about here. You can write any one. So I can say it's difficult to judge center of load. Part F, using only the apparatus provided for the experiment, explain briefly how you would determine the position of the center of mass of the meter ruler. This we did that day as well, which is that where the meter rule balances, so where the pivot is placed so that the meter rule balances. The rule balances is the center of mass. So it's exactly like that one. Kind of surprising because it's not like they both are variants of the same exam session, which makes sense if they are really that similar, but these are actually two different sessions. Again, this question is also very similar. Student investigates the resistance of a resistor wire. So there is the power supply, ammeter, sliding contact, and a resistance wire. Student places a sliding contact C at a distance L equals 20 cm from V. So this is 20 cm. He measures the potential difference V across length L, measures the current I, meters are shown. You know the next step will be to read the meters. So let's zoom in a bit more here. So this reading, if you look at this, so right in the middle of 0.6 and 0.8 would be 0.7. So 0.72, 0.74, 0.76 amperes. And if we look here, so this is exactly in the middle. So this would be 0.50 volts, right? 0.76 amperes. Where is my I reading? All right, so we have to write it here. 0.76 amperes. And the potential difference was 0.5 volts. Calculate and record in table 2.1 the resistance R of 20 cm of resistance wire. So use R equals V over I. So I just do 0.5 divided by 0.76. Turns out to be 0.66, right? So I can write it to 0.66. So again, there's this reason that some people do have when they look at the mark schemes is that how many significant figures do we use for calculated values? And the actual answer to this is you can use equal or more than the least number of SF. So here, if I wrote this as 0.5, which is 1 SF, this is 2 SF. So I can give this to, according to the least number of SF, I can give this to 1 or to 2 SF. But in this case, the examiner was also willing to award 3 SF because this is something which, what I'm telling you, this is from A levels. So it was also willing to give marks for this. And you can also see here that the column headings are missing. So that's also something we'll have to do. Calculate and record in the first row of the table R over L for 20 cm. So my answer, I just divide by 20, which is 0.03289. So 0.033 is what I'm getting, right? So again, I've used this idea that use the least number of SF. So you can give this to 1 or to 2 SF. This is what I get. All right. So that's my answer here. Next step is to complete the column heading. So voltage is in volts, resistance is in ohms, and ohms divide by length, but the length here was per centimeter. So you can write it like this, or I just remembered I'm teaching O level, so ohms per centimeter. You can also write it like this. Complete the column headings, done. Student repeats the procedure using L equals 60 and L equals 100 centimeters. Readings and results is shown. Look carefully at the values of R over L in table 2.1. Write a conclusion about the relationship between R and L. So if you look here, so R over L values are nearly constant, right? So you know that this is the definition of direct proportion. If you have two things, the ratio of which is constant, this means they're directly proportional. So you can say that R is directly proportional, or you can also just say proportional to L, right? Because you guys have given your math paper, you know this. Similarly, for inverse proportion, the idea is that the product of two things is the same. Justify your conclusion by reference to the result. So I'll say that R over L, this ratio has a constant value. For inverse proportion, the product would always be the same. Use values in 2.1 to estimate the resistance of 2 meters of the resistance wire. So 2 meters, right? So 2 meters, and because our R over L values were in centimeters, so I would have to convert this, right? So this is 2 meters of the resistance wire. So 2 meters would be 200 centimeters. So this is my R over L value, which was 0.035 or 0.033. Because you had two of the same values, you can take any one, right? All of these. So you could have taken either of these values for working. And then you multiply, because this is resistance per unit length. So this is ohms per centimeter. You multiply by the length, which is 200 centimeters. So you can see that you get your ohms back again. So 0.035 times 200 is 7 ohms, 7.0 ohms. Let's write it like this, because this should also be 2SF. A student investigates the magnification of the image produced by a lens. 3.1 shows the setup. Again, this is also the same question as was there. Measure the height h naught of the illuminated object. Last time I did do the experiment, this time I couldn't. So h naught turns out to be 1.5 centimeters. This is exactly the value the examiner wants from you. 3.1 is drawn to 1/10 of scale. On 3.1, measure the distance u. So this distance u turns out to be, so just measuring this is, this turns out to be 2 centimeters. And also, if you're smart, you can also reverse engineer this, because you know that if it's 1/10 of the scale, so the actual value would be 10 times that, which is given in the next part of the question, which is 20 cm. Student places the lens at the distance from the illuminated object. He moves the screen slowly until a clear focused image is formed. He measures the distance v between the center of the lens and the screen. On 3.1, this distance is represented to scale by the distance v. Use 3.1 to determine the actual distance between the center of the lens and the screen. Show your working. So this value actually turns out to be 8 cm. And then to convert this to its actual value, multiply by 10. This should be 80.0 centimeters. Right? So 8 was your measured value in this case, and you multiply by 10. Calculate and record in 3.1 the magnification m using m equals v over u. All right, so I think we also had to record this value. M equals v over u. Yeah, so we do have to use this value. So v is our 80.0. So m from here turns out to be 80 over 2, which is 4.00, if you write it like this. And hi is given, h0 we just found out, which is 1.5. So it also says the student measures the height of the image that is formed on the screen. The reading is shown. Calculate and record in 3.1 hi over h naught. So hi, the image height is 5.9, and above we found 1.5. So this turns out to be 3.93. So the student repeats the procedure using u equals to 30. Readings and results are shown here. And another student suggests that the magnification is equal to hi over h naught. You know by theory this is supposed to be true. State whether the results agree with the suggestion. Justify your statement by reference to the results. So I can visually see, and my calculations will show that yes, they are equal. So yes, they are equal, and I'll use the percentage difference idea here. So if I do 4 minus 3.93 divided by 3.93, times 100, I'm very certain my answer is going to be less than 10%, right? So I can say that this value, these are within 10%, so equal. I could have also done the same thing with the second set of values. So within 10%, so equal. Suggest how you would continue to use the same apparatus to test the suggestion that the magnification M is equal to the ratio HI over H naught. Why do we write in the planning experiment that you should take at least 6 values? Is because 2 values are not sufficient. And when you have 6 values, then what you can do is you can make a graph, right? So if you take different sets of values of U here, you also look here, you just have 20, 30, you take 40, 50, 60, 70, 80. So you have many more values and then you can make a graph. So for different U values, obtain a total of at least 6 readings and draw a graph. All right, question 4. Student investigates the time taken for the water to evaporate to dryness when heated from above. 4.1 shows the setup. The power of the heater is constant. The following is also available: supply of water at room temperature, meter ruler. So you have an infrared heater which is connected to the power supply. You have a shallow dish in which water is kept. And as you can see, this shallow dish is pretty wide. All right. Plan an experiment to investigate how one factor affects the time taken for the water to evaporate. Now this is up to you as to what factor do you want to see that how that changes. All right. So how this evaporates. So it's up to you if whatever you want to do this with. For example, the first thing that comes to mind when looking at this for me is the volume of the water, right? Or you can also do this that, for example, if you change the height of the heater above the water, this would also be fine. You do not need to write about safety, state any additional apparatus required, explain briefly how you would do the investigation, state the key variables you would keep constant, draw a table of values, explain how you would use your readings to reach a conclusion. Again, first let's identify our independent, dependent, and control variables. Again, we have to observe how the time taken varies. So obviously we would need a stopwatch here, right? So again, this is our dependent variable here, and our independent variable for my experiment, for my description, is going to be the volume of water, right? So I'll say this in defining the problem. I'll say that I will vary the volume of the water and measure the time taken for the water to evaporate completely, right? So this is my first step where I talk about the dependent, independent variables. So I vary the volume of water in the dish and measure the time taken for the water to evaporate. Now about the control variables, what should be kept constant is I would first off say that the power of the heater should be kept constant, but this is already given here, right? So as we just talked about, we can say that the height of the heater above the water, right? Or we can also say that because we know evaporation is also affected the by the movement of wind, I can also say that it should be there should be the same amount of wind that should not change to affect our readings, right? The surface area of the water, that can also be written, right? Because surface area also affects the rate of evaporation. If I take a different dish in which I have a lesser area exposed, that would reduce the evaporation. So out of these, you can write any two. So I'll say keep the movement of wind and the area of the water exposed constant. Right, so only at this point I've secured like half of the marks almost, because I've talked about the dependent, independent variables. Later, I'll also need to talk about the stopwatch. In IGCSE, you might have seen that there is this trend where they intentionally miss out on an important piece of apparatus, and then you have to describe this later. For example, in this one, it was explicitly asked, state any additional apparatus required. This is usually not given in our O-level papers. Everything that we need is given in the description. So we'll say that we will use a stopwatch to measure the time for the water to evaporate. And yeah, again, we would also talk about the number of readings which are to be taken. So we'll say that, for example, we use 6 different volumes of water and measure those 6 times for the water to evaporate. So I'll also say here then that measure time for evaporation using a stopwatch. And then I'll say repeat for 6 different volumes of water. Right, so then you'll have your 6 different readings here basically. And then you have to obviously discuss the table of values here. So table of values, again, you'll really have only a few things, which is that if you're talking about all the water evaporating, you just have to have the time and you'll have to have the volume, right? You just need these things. So if I make this, let's say, and again, this is not important, serial number, this is the volume of the water, an appropriate unit, could be meter cube, could be cm cube, and time, again, usually seconds or minutes will work. And this is what your table of values look like. So these are our values. And then the last part, again, you know that there's always the same generic answer to it every time. So plot a graph of volume versus time. To reach conclusions. Right, so that's how you secure all your marks here. Also, another key difference that you guys must have noted while doing these IGCSE papers is that in our syllabus, the planning question was always 6 marks, and here it's 7 marks. And the 7th mark is just for that additional piece of apparatus that you have to identify, right? Nothing else. So yeah, I guess all of you are now comfortable with the planning question. It's not really all that difficult. It's pretty much the same steps that you have to follow for many different experiments. All right. So if you guys have no questions, we can end this here. So 1 hour, but I'm pretty sure we got done in like 40 minutes. And that was despite me feeling that I did take a lot of time on plotting. All right, guys. So that's it for now. Best of luck. And then inshallah, let's meet tomorrow. Bye bye.